Okay, so imagine this for a second. A planet, life is just thriving, oceans are teeming, forests everywhere. Then, boom, suddenly, like really dramatically, 96% of all the life in the sea just vanishes.
Gone, yeah.
And not slowly, not over millions of years, but geologically speaking, like snap, in the blink of an eye.
It's almost instantaneous, yeah.
Think about that scale. An entire planetary ecosystem just almost wiped clean.
It's staggering.
What kind of, unimaginable event could possibly cause that kind of devastation?
Right.
And maybe even more importantly for us now, what can these ancient catastrophes, these moments when life on Earth basically stared into the abyss, what can they teach us about the challenges we're facing right here, right now?
That's the core question, isn't it?
Welcome to the Deep Dive. Today, we're really going on a journey back through Earth's most cataclysmic moments, the Big Five Mass Extinctions.
We're going to dig into the science, the paleontology, the geology, sift through all that data.
Yeah, and not just pull out facts, but try to find the deeper insights, the lessons these ancient disasters hold for us.
Exactly. So our mission for you, our listener, is to really unpack these huge moments in Earth's history. We want to delve into, what caused them, what were the primary drivers, and then look at the consequences, the devastating ripple effects across the globe, and also, how did life eventually come back? Because it always did, somehow.
Right, the recovery story.
And by looking back at these periods of, profound planet-altering change, the hope is we gain some really crucial insights into the biodiversity crisis we're facing now.
Yeah, maybe get a better handle on it.
Yeah, equip you with a solid framework, not just for understanding, but maybe for addressing some of these really complex modern-day challenges that are looming so large.
So that's why this deep dive feels so, vital right now. Because what we're finding, what the science shows, is that the fossil record isn't just some dusty old archive.
No.
It's actually this incredibly powerful tool. It can be predictive, even diagnostic for our time.
It really can. You see these startling parallels between ancient natural forces, volcanoes, asteroids, and the kind of impact humans are having today.
It's kind of uncanny sometimes. So this isn't just a history lesson.
No, it's more like an exploration. We're looking at planetary resilience, how much can the Earth take? We're looking at ecological tipping points, and these often uncomfortable echoes from the deep past that are, frankly, resonating right now.
Okay, so let's dig in. Where do we start? Before we jump back millions of years, maybe we should just clarify what we mean by mass extinction. It's a term we hear a lot, but scientifically it's quite specific, right?
That's a really crucial starting point.
Yeah.
So a mass extinction, scientifically speaking, means a widespread and, importantly, rapid decrease in the Earth's biodiversity.
Okay, widespread and rapid.
Exactly. You see this sharp, dramatic fall in both the diversity, meaning the number of different species, and just the sheer abundance of life, specifically multicellular organisms.
So lots of species disappearing and fewer individuals are the ones left.
Pretty much. And what makes it really distinct is the scale and the speed. It's fundamentally different from what scientists call the background extinction rate, or BER.
The BER, and that's like the normal everyday turnover, the natural rate at which species disappear over huge stretches of time.
Precisely. Think of the background rate as the natural hum of life cycles. It's the steady, gradual pace where some species naturally go extinct as maybe others evolve, or environments slowly change.
Kind of the cost of doing business for evolution.
Sort of, yeah. The most conservative estimates, the really careful ones, put the BER at about 1 extinction per million species per year. So 1 EMSY.
1 per million per year. Okay.
Yeah, so if you imagine Earth has, say, 1 million species, just for argument's sake, then on average, you'd expect one of those to naturally go extinct each year. It's part of the evolutionary process. It's slow, almost unnoticeable on human timescales.
But mass extinctions are different.
Yeah. Totally different. They are catastrophic interruptions. They're like a sudden, jarring silence in that natural hum. An overwhelming number of species vanish all across the globe in multiple ecosystems relatively quickly.
So not just a local problem, but a global reset button. Almost.
That's a good way to put it, a planetary reset. And over the last, say, 540 million years, that's the Phanerozoic eon, the time when complex multicellular life really took off and left us a good fossil record. This normal, gradual background process got dramatically interrupted by 5 of these exceptional catastrophes. And these are the events we now call the Big Five.
The Big Five. Okay, let's list them out.
All right, so going chronologically. First up is the end Ordovician extinction. That was roughly 440 million years ago.
Okay.
Then you have the late Devonian extinction, around 370 million years ago.
Got it.
Next, the big one, the end Permian extinction. That's the one often called the Great Dying, about 252 million years ago.
The Great Dying. Sounds ominous.
It was. Then, the end Triassic extinction, approximately 201 million years ago. And finally, the one most people know, the end Cretaceous extinction, about 66 million years ago. That's the dinosaur killer.
Wait, the asteroid one.
Well, mostly. We'll get into that. But yeah, each of these events was just immense in its destructive power. They wiped out a huge majority of species living at the time and fundamentally rewired Earth's biosphere.
We're not talking about just a bad century here.
No. These were episodes of profound planetary upheaval. They reshaped the entire course of evolution for millions and millions of years afterwards.
And that really brings us back to the point of this deep dive, doesn't it? We're not just listing disasters.
Exactly.
We're trying to pull out the lessons. What can analyzing their causes, the mechanisms, the way recovery happened, what does that tell us?
Because those insights aren't just academic curiosities, they feel incredibly relevant, almost urgent right now for understanding and maybe even tackling the current biodiversity crisis.
So the fossil record isn't just history.
It's like a playbook, a diagnostic tool. It shows us patterns, vulnerabilities, consequences. It's vital data for our present and our future.
Okay. So looking across these big five, what's really striking is that they had different triggers, right? You mentioned volcanism, asteroids, maybe ice ages, very different starting points.
Very diverse triggers, yeah.
But despite that diversity, was there some kind of common thread?
Yeah.
Like a shared mechanism or a planetary weak point they all exploited?
That's a fantastic question. And it really gets to the heart of why they were mass extinctions. You're right. It wasn't usually just one isolated thing.
Yeah.
Instead, the evidence overwhelmingly points towards a cascade of rapid, synergistic environmental stressors.
Synergistic meaning?
Meaning the combined effect was way worse than just adding up the individual problems. Think of it like a deadly cocktail. Multiple pressures hitting at once or in quick succession.
Like a 1-2 punch or a 1-2-3 punch.
Yeah, exactly. You might have warming, plus ocean acidification, plus oxygen loss all hitting together. And these rapid, interconnected changes just happen too fast. Life couldn't keep up. It couldn't evolve fast enough, couldn't migrate away quickly enough.
Pushed ecosystems past their breaking point.
Precisely. Past their tipping points, leading to this global ecological collapse. It's like a complex machine. One part fails, it triggers another failure, which triggers another, until the whole system just grinds to a halt.
Okay, let's start our journey properly then with the first of the big five, the Ordovician Silurian extinction, way back about 440 million years ago. Now, this one's often called the glacial paradox, which sounds intriguing. What was driving this ancient catastrophe?
Yeah, the Ordovician Silurian was driven by something truly massive geologically, a major continental glaciation event, an ice age. And linked to that, a huge global fall in sea level.
An ice age causing an extinction. Yeah.
Well, the leading theory is that the supercontinent Gondwana, which back then included bits of South America, Africa, Antarctica, Australia, India, it basically drifted over the South Pole.
Okay.
And as this huge landmass sat over the pole, massive ice sheets started to form, way bigger than anything we have today, locking up enormous amounts of Earth's water.
Right, like Antarctica and Greenland today, but much bigger.
Much bigger. And this process kicked off dramatic global cooling and, critically, this massive drop in sea level. We're talking maybe up to 100 meters.
100 meters. Wow. Okay, what does that do to life, especially marine life, which was pretty much all the complex life back then, right?
Exactly. Life was overwhelmingly in the oceans,
Yeah.
and the consequences of that sea level drop were just devastating. The main killers here were habitat loss and just severe shrinking of where things could live.
So the shallow seas just disappeared.
Pretty much. Shallow marine species, which were incredibly diverse in the Ordovician period, literally had their homes shrink dramatically or vanish entirely as the seas retreated. Imagine all those thriving coastal ecosystems, the continental shelves, suddenly high and dry.
Can you give us an idea of what kind of creatures were hit hardest? What were the main victims?
Sure. Estimates are that up to 85% of those shallow marine species died out. We're talking iconic groups like trilobites, those segmented armored arthropods, everywhere back then.
Sort of beetle-looking things.
Kind of, yeah. They took a massive hit. Also, brachiopods, they look a bit like clams but aren't closely related. They were hugely abundant filter feeders and they suffered badly. And bryozoans, these tiny colonial animals that built intricate, lacy structures like underwater corals almost.
Moss animals, right.
Exactly, moss animals. They were major reef builders in some places. All these dominant groups were decimated. It completely changed the structure of ocean life.
So, massive glaciation, cooling, sea level drop.
Yeah.
But what kicked off the glaciation in the first place?
Yeah.
Just Gondwana drifting south.
Yeah.
Or was there something else? Is that settled science?
Well, that's where it gets interesting and highlights how complex these Earth systems are. There isn't one single universally agreed upon trigger. Gondwana drifting south is the main framework, but what tipped it into full-blown ice age?
Right.
Some evidence points to maybe a volcanic trigger. Increased volcanic activity could have initially messed with the atmosphere. But there's another really compelling idea.
Which is?
The rise of the first land plants.
Plants caused an ice age. How?
Well, the idea is that as these early plants started colonizing the bare continents during the Ordovician and Silurian, they would have started drawing down huge amounts of carbon dioxide from the atmosphere through photosynthesis.
Okay.
CO2 is a potent greenhouse gas. So if plants are pulling massive amounts out of the air, that could lead to significant global cooling, potentially enough to trigger or amplify the glaciation already primed by Gondwana's position.
Wow. So the greening of the land might have frozen the planet? That's paradoxical.
It is, and it leads us back to why it's called the glacial paradox, because it's the only one of the Big Five clearly linked to a major ice age and global cooling. Most of the others, as we'll see, are associated with warming.
So what's the big lesson from this cooling-driven extinction, this paradox?
I think the lesson is really profound, especially for us today. It tells us that the primary driver of mass extinction isn't necessarily the direction of climate change, whether it gets hotter or colder. It's the rate and magnitude of the change, how fast and how big the shift is. A rapid, major swing in either direction, hot or cold, creates conditions that species, especially those stuck in certain areas or with specialized needs, just can't adapt to quickly enough. Their whole world changes faster than they can cope.
So it's the speed of the change that's the real killer.
That seems to be the key takeaway. And this event also perfectly shows that cascading model we mentioned earlier. You have one big geological event, Gondwana moving, maybe volcanism, maybe plants taking off, and that triggers a chain reaction. Ice sheets form, sea levels plummet, ocean currents shift because the geography and temperatures change.
One domino knocks over the next.
Exactly. A cascade of habitat destruction and environmental stress. And that ancient cascade feels unnervingly similar to the modern crisis, doesn't it? Human CO2 emissions are kicking off a similar cascade now.
Right.
Rapid warming, ocean acidification, oxygen loss. Different initial trigger, same cascading dynamic of rapid change.
Okay, moving forward in time, let's look at the late Devonian extinction, around 370 million years ago. Now, this one sounds different. Not a sudden shock like an asteroid, or even a relatively quick cooling like the Ordovician, but something longer.
Absolutely. The late Devonian wasn't a single sharp blow. It was more like a long, slow bleed. It actually unfolded in multiple distinct waves or pulses over several million years. A protracted chronic crisis.
Multiple ways.
Yeah, with the final really big pulse known as the Hangenberg event, right near the end of the Devonian period, around 359 million years ago. That one seems to have been particularly intense. But the key thing is this multi-pulse nature. It suggests the Earth systems were under sustained, intermittent stress for a very long time.
So what was causing this prolonged stress? What was the main problem during the late Devonian?
The leading hypothesis, the one with the most evidence, points primarily to the oceans running out of oxygen. Widespread marine anoxia.
Anoxia, a lack of oxygen.
Exactly. And in some cases, it might have even become euxinic, meaning the water became rich in toxic hydrogen sulfide. This created vast dead zones across the oceans, particularly on the seafloor and in shallower waters, where most marine animals just couldn't breathe. Imagine huge stretches of ocean becoming literally suffocating.
Okay, why would the oceans lose oxygen like that?
Well, the likely culprit seems to be a massive increase in nutrients washing into the oceans from the land.
Nutrients, like fertilizer almost.
Kind of, yeah. Especially phosphorus and nitrogen. And where were these excess nutrients coming from? Again, potentially the land plants.
Plants, again, they really stir things up.
They do. The Devonian period is often called the Age of Fishes, but it was also a time when land plants were really taking off. They were evolving deeper roots, bigger structures, forests were starting to spread.
Right.
This massive greening of the continents would have dramatically increased the rate of rock weathering and soil formation on land. More soil means more organic matter and nutrients getting washed into rivers and then out into the sea.
Okay, so more nutrients flow into the ocean. Then what?
Then you get huge algal blooms. Just like when fertilizer runoff causes algal blooms in lakes today, these massive blooms of algae thrive on the excess nutrients, but when they die and sink, the bacteria that decompose them use up enormous amounts of dissolved oxygen in the water.
Ah, I see. So the decomposition sucks the oxygen out.
Exactly, leading directly to widespread anoxia and those deadly marine dead zones. Now, there were other factors likely involved too, some evidence for global cooling episodes, sea level changes, maybe even volcanism or impacts contributing pulses of stress. But the anoxia seems to be the central theme.
So the very success of life on land, the plants, might have indirectly choked life in the sea. That's quite the feedback loop. Who were the main casualties this time?
The impact on marine life was, again, devastating, especially for organisms living on or near the seafloor, and particularly the reef builders. Estimates are around 70 to 85% of all aquatic species wiped out.
Reefs took a big hit again.
A massive hit. The great reef ecosystems of the Devonian, built by organisms like stromatoporoid sponges and rugose and tabulate corals, were utterly decimated. In fact, complex reef ecosystems essentially disappeared from the planet for millions of years after this extinction. That's a huge ecological void.
Wow, millions of years without reefs.
Yeah. Some other groups survived better, like crinoids, those feathery sea lilies, and certain types of brachiopods. Maybe they were more tolerant of low oxygen or had different feeding strategies that helped them cope.
This protracted multi-pulse nature you mentioned, it feels different from a single shock. What's the key lesson from a crisis that drags on, hitting in waves over millions of years?
I think the critical lesson from the late Devonian is that a slow, chronic crisis can ultimately be just as destructive, maybe even more insidious than a single sudden catastrophe. It shows that relentless ongoing pressure, even if it waxes and wanes, can grind ecosystems down.
Like death by 1,000 cuts.
Exactly. And the fact that it came in pulses might have been particularly damaging. Maybe ecosystems started to recover a bit between the stressful periods, but then another wave of anoxia or cooling hit, preventing a full rebound and making them even more vulnerable next time.
That sounds worryingly relevant to some of our modern problems.
Highly relevant. Think about chronic issues today, like ocean acidification, persistent plastic pollution, gradual habitat loss and fragmentation. These aren't single shocks. They are long-term, grinding stressors, slowly eroding resilience. The late Devonian warns us about the danger of these slow-burn crises.
And the land-sea connection, the plant runoff causing ocean problems.
That's another huge takeaway. The strong link between the greening of the land and marine anoxia back then is a direct historical parallel to modern eutrophication. Where agricultural fertilizer runoff or sewage causes algal blooms and dead zones in coastal areas today.
Right, like in the Gulf of Mexico.
Precisely. The late Devonian is a powerful reminder written in stone of how deeply interconnected Earth systems are. Changes on land, even seemingly positive ones like plant growth, can have profound destabilizing consequences for the oceans.
Okay, now we arrive at the heavyweight champion of extinctions, the Permian Triassic event, about 252 million years ago, chillingly known as the Great Dying. This wasn't just another mass extinction, was it?
No, not at all. This was, and it's hard to overstate this, the most severe extinction event in the entire history of complex life on Earth. It's the closest life ever came to being completely wiped out.
How bad are we talking? What are the numbers?
The numbers are just mind-boggling. Estimates suggest up to 96% of all marine species vanished. 96%.
Wow.
And on land, it wasn't much better. Maybe 70% of terrestrial vertebrate species disappeared. Insects suffered their only known mass extinction. Plants were devastated. It was a near total biological annihilation.
96% marine loss. That means only 4 out of every 100 species survived in the oceans. It's almost impossible to grasp.
It really is, and the scientific consensus on the primary cause is now overwhelming. It points to the Siberian traps, colossal flood basalt volcanism.
Siberian traps. Okay, tell us about those. Was this like one giant volcano?
Not quite. Think bigger, way bigger. The Siberian traps were a massive igneous province, a huge area in what's now Siberia, where enormous volcanic eruptions occurred, probably over a period of maybe 1 million years or so, maybe less, centered around 252 million years ago.
How big an area?
Imagine eruptions covering an area roughly the size of Western Europe, or maybe even the continental U.S., just spewing out vast quantities of lava, layer upon layer. But critically, it wasn't just the lava.
It was the gases again. like in the other events.
Exactly. These eruptions released absolutely immense volumes of gases into the atmosphere. We're talking catastrophic amounts of carbon dioxide, methane, which is an even more potent greenhouse gas in the short term, sulfur dioxide, chlorine, fluorine, just a toxic cocktail on a planetary scale.
Okay, so how did this massive injection of volcanic gases cause such an almost complete wipeout of life? What were the killing mechanisms?
It triggered a devastating cascade, a runaway effect that just spiraled. The most immediate and direct impact was extreme global warming, driven by all that CO2 and methane.
How hot did it get?
Models and geochemical evidence suggest it got incredibly hot, incredibly fast. Equatorial ocean surface temperatures might have soared past 40 degrees Celsius.
40 degrees Celsius. That's over 100 Fahrenheit. That's like lethal hot tub water.
Exactly. Way beyond the tolerance of most marine organisms. Think about what extreme heat does to proteins. It denatures them. It basically cooks organisms from the inside out. This heat stress alone would have been catastrophic, especially in the tropics.
And it didn't stop there, right? This sounds like the ultimate example of those synergistic effects, the deadly cocktail you mentioned.
Absolutely. The Great Dying is the terrifying poster child for the synergistic cascades. So you have the lethal heat, but then warmer water holds much less dissolved oxygen.
Right.
And at the same time, when organisms get hotter, their metabolism speeds up, meaning they actually need more oxygen to survive.
Oh, wow. Less oxygen available, but they need more. It's
Yeah.
a death trap.
A lethal double whammy. It created widespread ocean anoxia, just like in the Devonian, but likely even more severe and widespread. The fossil record points to vast swaths of the ocean becoming not just anoxic, but sulfidic, rich in poisonous hydrogen sulfide, as normal ocean circulation patterns broke down due to the heat.
Sulfidic, like rotten egg gas. Poison.
Exactly. Hydrogen sulfide is toxic to most complex life. So you have heat stress, oxygen starvation, and toxic water. And on top of all that, all the CO2 being absorbed by the oceans would have caused rapid and severe ocean acidification.
Dissolving shells and skeletons.
Precisely. Organisms that build shells or skeletons out of calcium carbonate, like corals, mollusks, plankton, they would have struggled and unable to build them. It was a multi-pronged assault on life from every direction.
This event, the Permian Triassic, it honestly sounds like the most direct and frankly frightening comparison to what we're potentially facing now with climate change. What's the absolute core lesson here that resonates today?
The core lesson is the terrifying power of that synergistic cascade. How a single massive initial driver, in this case, the Siberian Trap's volcanism, can trigger a series of interconnected, self-reinforcing feedback loops.
Like a chain reaction getting worse and worse.
Exactly. CO2 causes warming. Warming reduces oxygen. Low oxygen promotes sulfide production. Maybe methane gets released from the seabed, causing more warming. It spirals out of control. This ancient cascade is a chillingly precise mirror of modern climate concerns. We're seeing multiple linked stressors now: warming, acidification, deoxygenation, habitat loss, all hitting ecosystems simultaneously. The Permian warns us, in the starkest possible terms, how these interacting stressors can multiply their impacts, leading to outcomes far more catastrophic than any single factor alone might suggest. It shows us what happens when you push planetary systems past multiple tipping points at once. We are, in a very real sense, running a similar, albeit hopefully smaller scale, experiment right now.
Okay, moving on from the sheer horror of the Permian, let's get to the next event, the end Triassic extinction, around 201 million years ago. This one is also linked to massive volcanism, but a different set of eruptions tied to another huge geological event, right?
That's right. This extinction lines up perfectly with another colossal flood basalt event, the Central Atlantic Magmatic Province, or CAMP.
TMP.
This was another enormous outpouring of lava, covering huge areas across what are now North and South America, Africa, and Europe, basically, the continents surrounding the budding Atlantic Ocean. And this volcanism was directly triggered by the initial stages of the breakup of the supercontinent Pangea.
Pangea breaking up. So as this giant landmass started to rip apart, forming the Atlantic, volcanoes erupted.
Exactly. As Pangea stretched and thinned, huge fissures opened in the Earth's crust, and magma poured out for hundreds of thousands of years. It was a key moment in shaping the modern world map, and it came with a hefty dose of volcanic gases.
So similar story to the Permian then. Massive eruptions, huge CO2 release, global warming.
Pretty much the same mechanism, yeah. The CAMP eruptions released massive amounts of greenhouse gases, mainly CO2, into the atmosphere. This led to another significant episode of rapid global warming and related changes in the oceans like acidification and deoxygenation. Maybe not quite on the same apocalyptic scale as the Permian Siberian traps event, but still a major global crisis.
And who were the main victims this time? Did it hit marine life as hard?
It certainly hit marine life hard, with significant losses among ammonites, bivalves, and reef organisms. But perhaps the most impactful losses, from an evolutionary standpoint, were on land. This event really hammered many groups of large archosaurs.
Archosaurs. Those are the group that include crocodiles and dinosaurs, right?
And pterosaurs, yes. Back in the late Triassic, dinosaurs were around, but they weren't necessarily dominant everywhere. There were other large archosaur groups, sometimes broadly called crocodile-like archosaurs, that were major players.
Like what, for example?
Well, one really prominent group that got wiped out were the phytosaurs. Superficially, they looked incredibly similar to modern crocodiles. Long snouts, powerful bodies, aquatic predators. But they weren't direct croc ancestors, it was convergent evolution. They had their nostrils way up high on their head, near their eyes. They were major predators in rivers and lakes. They vanished. Other large terrestrial archosaurs, some big amphibians, even some early mammal relatives also took a big hit. But here's the twist.
The dinosaurs didn't get hit as hard.
It seems dinosaurs, or at least certain lineages of dinosaurs, weathered the storm much better than their main competitors, like those large phytosaurs and other archosaurs. And this is where the end Triassic extinction becomes really fascinating. It created a massive opportunity.
You mentioned this term before, ecological release. This is what happened here.
Precisely. This is a textbook example of ecological release, with many of the dominant land animals, especially the big predators and herbivores, suddenly removed from the picture. A whole lot of ecological jobs or niches became vacant.
The competition was gone.
Exactly. And who was ready and waiting to step into those empty roles? The dinosaurs. This extinction event essentially cleared the playing field, paving the way for the dinosaurs to rapidly diversify and rise to dominance in the following Jurassic and Cretaceous periods, the famous Age of Dinosaurs.
So it wasn't just the dinosaurs were inherently better and outcompeted everyone slowly.
Not necessarily, no. Their rise wasn't just a gradual victory in a long, competitive slog. It was significantly boosted, maybe even primarily caused, by this catastrophic extinction event that conveniently removed their main rivals. The catastrophe reshuffled the deck, and dinosaurs happened to hold the winning hand afterwards.
So the crucial lesson here is about who survives, isn't it? It's not always the fittest in the old world.
It's often about who is either lucky enough to survive the crisis, or perhaps happens to have traits that are advantageous in the new post-crisis world. The end Triassic really shows how big-picture evolution, macroevolutionary trends, aren't just driven by slow, steady competition. They can be radically redirected by external shocks, by these non-biological catastrophes. The winners emerging from an extinction aren't always the ones who were top dog before. They're the ones who could handle the chaos or exploit the aftermath. It tells us that contingency, chance events, play a huge role in the history of life.
All right, let's move to the final and probably most famous of the Big Five, the Cretaceous Paleogene, or KPG extinction. About 66 million years ago. This is the one that gets all the press, the end of the dinosaurs.
That's the one.
And intriguingly, this extinction event happened right around the time of two potentially catastrophic global events, leading to quite a bit of scientific debate over the years, didn't it?
It certainly did. For a long time, there was a really lively, sometimes quite heated debate, because the KPG boundary coincides almost perfectly with two massive geological events. The Chicxulub asteroid impact in Mexico's Yucatan Peninsula.
The famous asteroid.
The famous asteroid. And also a period of intensified, enormous volcanic eruptions on the other side of the world in India, the Deccan Traps.
Deccan Traps, another one of these huge flood basalt provinces.
Exactly. Similar in scale to KMMP, or maybe even parts of the Siberian Traps. So the question became, was it the asteroid? Was it the volcanoes? Or was it some combination of both that killed the dinosaurs and so much other life?
Okay, let's start with Chicxulub. This is now pretty widely accepted as the main trigger, right? What's the killer evidence?
The evidence for the Chicxulub impact being the primary cause is now incredibly strong, really compelling, and accepted by the vast majority of the scientific community. The smoking gun, perhaps the most famous piece, is the iridium anomaly.
Iridium. That's rare on Earth, right?
Extremely rare in Earth's crust, but much more common in asteroids and meteorites. And scientists found this thin layer of clay right at the KPG boundary all over the world that is dramatically enriched in iridium, a global fingerprint of extraterrestrial material raining down.
Wow. Okay. What else?
There's more. We find shocked quartz grains in that boundary layer. Quartz is common, but under the immense pressure of a massive impact, its crystal structure gets deformed in a unique way. You only see that kind of shocking from impacts or nuclear explosions.
Right.
And we also find tektites. These are little glassy beads or blobs formed when rock is melted by the impact's heat, flung high into the atmosphere, and then solidifies as it rains back down. Finding iridium, shocked quartz, and tektites together, globally, right at the extinction boundary, and centered around the massive Chicxulub crater. It paints a very clear picture.
So how did the impact actually cause the extinction? What was the mechanism?
The immediate effects of the impact itself, the blasts, tsunamis, would have been devastating regionally. But the global killer was the aftermath. The impact vaporized rock and threw truly enormous amounts of dust, soot, from wildfires ignited by the impact, and sulfur aerosols high into the atmosphere, blocking sunlight.
An impact winter.
Exactly. A prolonged period of darkness and intense cold, lasting months, maybe years. This would have shut down photosynthesis, killing plants on land and phytoplankton in the oceans, the base of almost every food web. Widespread starvation, ecosystem collapse. That's a leading theory for the global extinctions.
Okay, but what about the Deccan traps? The volcanoes were erupting around the same time. Don't they play a role? Is that debate completely over?
Well, the debate has shifted. While the impact is seen as the primary knockout blow, the role of the Deccan traps is still actively researched and discussed. It's more nuanced now. Some scientists argue the massive Deccan eruptions, releasing CO2 and sulfur dioxide, could have caused significant climate stress before the impact, maybe weakening ecosystems and making them more vulnerable.
So pre-stressing the system.
Possibly. Others argue the volcanic gases, especially sulfur, could have contributed to the cooling or ocean acidification after the impact, prolonging the crisis. However, a key argument against the volcanoes being the main driver is the apparent speed of the extinction.
It looks instantaneous in the rock record.
Geologically speaking, yes. The extinctions seem to happen very sharply and synchronously around the world right at the impact layer. That pattern fits much better with a sudden, catastrophic shock like an asteroid impact, rather than the more gradual, though still massive, effects expected from volcanism spread over hundreds of thousands of years.
Interesting. And I heard there's even a counterintuitive idea about how the volcanoes might have interacted with the impact.
Yes, this is a fascinating recent twist. Some climate modeling studies suggest something quite paradoxical. While the impact caused rapid, intense cooling, the impact winter, the long-term effect of the Deccan traps releasing CO2 would have been warming.
Okay.
So some research suggests the background warming from the Deccan volcanism might have actually partially offset or buffered the extreme cold of the impact winter. In this view, the volcanoes might have weirdly reduced the overall severity of the extinction slightly, rather than making it worse.
Wow, okay. So the interaction is complex.
Very complex. It really highlights how intricate Earth's climate system is, with different factors pushing and pulling on different timescales.
So pulling it all together, what does this most famous extinction, the KPG, teach us, especially compared to the others?
I think the KPG event really underscores the danger of a sudden, unpredictable black swan type of catastrophe, a bolt from the blue that changes everything instantly. This contrasts sharply with, say, the long, drawn-out crisis of the late Devonian.
Right, different tempos of disaster.
Exactly. It shows that existential threats can manifest at vastly different speeds, from a slow burn over millions of years to an apocalyptic Tuesday afternoon. This emphasizes the need for resilience to both long-term trends and sudden shocks. And the whole debate around the Deccan traps teaches us another crucial lesson.
Yeah.
Just because two potential stressors happen around the same time doesn't mean they automatically add up to make things worse.
They aren't always synergistic in the same direction.
Precisely. Sometimes their effects can be complex, even opposing, depending on the specific mechanisms and timescales. The idea that the volcanic warming might have slightly counteracted the impact cooling is a prime example. It really forces us to dig deep into the specific details, the physics and chemistry, to understand the true causal links. We can't just assume crises always pile on top of each other linearly. Sometimes the planetary system reacts in more complicated ways.
Okay, so we've walked through these 5 apocalyptic events, almost unimaginable destruction. But life somehow persisted. What happens after the dust settles or the oceans warm up again? What does the fossil record tell us about recovery?
Yeah, the recovery phase is just as fascinating in its own way. Life is incredibly resilient, but recovery from these mass extinctions is almost never a quick bounce back. It's typically a slow, protracted process, often taking millions, sometimes even tens of millions of years.
Millions of years to recover.
Think of it as the Earth slowly healing, ecosystems gradually rebuilding. And this recovery process is driven by what some call the phoenix effect.
The phoenix effect, rising from the ashes.
Exactly. The surviving species, those few lineages that manage to scrape through the bottleneck, find themselves in a radically changed world with lots of empty space, ecologically speaking. This vacated ecospace creates huge opportunities.
Less competition, new resources available.
Right. So these survivors often begin to flourish, diversify, and innovate, evolving new forms to fill those empty ecological roles. The overall pattern of biodiversity you see in the fossil record is governed by this balance, the rate of extinction versus the rate of speciation, the origin of new species.
So after a mass extinction wipes out species, recovery happens when speciation eventually starts outpacing extinction again.
That's the basic idea. Extinction rates spike during the crisis, biodiversity plummets. Then, in the aftermath, extinction rates hopefully fall back down, and speciation rates gradually pick up among the survivors, slowly refilling the biosphere.
And you said these recovery periods can take a long time. Are they all roughly the same length, or does it vary?
It varies dramatically. It seems to depend heavily on the nature and severity of the extinction event itself and the state it left the planet in. Some recoveries were much, much slower than others, leaving a really long-lasting scar.
Like which ones?
Well, take the aftermath of the Permian extinction, the Great Dying. One really stark piece of evidence for how bad things were, especially on land, is something called the coal gap.
The coal gap. What's that?
For about 5 to 10 million years after the Permian-Triassic boundary, you find virtually no coal deposits being formed anywhere in the world.
And coal comes from plants, right? Dense vegetation, swamps.
Exactly. Coal forms from huge accumulations of dead plant matter. So a global coal gap strongly suggests a catastrophic loss of plant life worldwide. Forests, swamps, peatlands, the ecosystems that produce coal must have been absolutely decimated.
Wow. So the base of the food web on land was just hammered.
Hammered. It tells us that the recovery of complex terrestrial ecosystems, dense forests, and the like was exceptionally slow and drawn out after the Permian. It might have taken up to 10 million years for things to really get back on track. That shows how an event that fundamentally guts the primary producers can have incredibly long-lasting ecological consequences.
Any other examples of slow recovery?
Yes, the recovery of marine life after the late Devonian extinction, particularly after that final Hangenberg event pulse, seems to have been even worse. It's often described as exceptionally and curiously slow.
How slow?
Potentially lasting more than 20 million years. That might be the longest post-crisis recovery slump following any of the Big Five.
20 million years. Why so long?
Sure.
Is it clear?
The precise reasons are still debated and frankly described as little studied and unknown in some research. But potential factors include maybe persistently cool global conditions lingering after the glacial pulses associated with the Hangenberg event. Or perhaps there was some kind of continued chronic environmental stress, maybe lingering low oxygen levels in parts of the ocean that just kept suppressing diversification for a very long time. Unlike, say, the recovery after the KPG impact, which, while taking millions of years, seems relatively brisk compared to the Devonian aftermath.
The length of this aftermath, this recovery time, that feels like a really critical lesson for us today, doesn't it? Especially thinking about the potential impacts of our current actions.
It absolutely is. It's one of the most sobering lessons. The duration of the recovery period seems directly linked to how the crisis damaged the Earth system, a crisis that destroys the very foundation of the food web, like the Permian coal gap suggests, or one that creates chronic, ongoing stress that doesn't really let up, as possibly happened after the Devonian, can prevent a full recovery for entire geological epochs. We're talking tens of millions of years.
So the implication?
The implication is that the current human-driven crisis, being a multifaceted chronic stressor involving warming, acidification, habitat loss, pollution, could potentially trigger a similarly prolonged recovery period for global biodiversity. Even if we slammed on the brakes today, the ecological and evolutionary scars could last for an incredibly long time. The damage we're doing now might echo for millions of years.
That's a heavy thought. So during these crises, who actually makes it through? Was survival just a lottery, completely random? Or were there traits that made some species more likely to survive.
It definitely wasn't purely random. The fossil record is quite clear on this. Certain traits significantly boosted a species' chances of survival.
Yep.
Two factors consistently seem to pop up as being really important.
Okay, what are they?
First, having a wide geographic range, being spread out across a large area.
Why does that help?
Well, species with small, localized populations may be restricted to a single island or one mountain range, or a specific reef system, were incredibly vulnerable. A localized disaster, like a volcanic eruption nearby, or a regional climate shift, or habitat destruction in that one area, could wipe out the entire species in one go.
Right, all your eggs in one basket.
Exactly. But if your species was spread across multiple continents or vast stretches of ocean, even if some populations were hit hard, others might survive elsewhere, providing a reservoir for future recovery. Being widespread was a huge advantage.
Okay, wide range. What's the second trait?
Being a generalist rather than a specialist.
Meaning?
Meaning being adaptable. Species that could eat a variety of different foods, tolerate a wider range of temperatures or environmental conditions, or live in several different types of habitats tended to fare much better than specialists.
Specialists being those finely tuned to one specific food source or environment.
Right. Think of a koala that only eats specific eucalyptus leaves, or a fish adapted only to a very particular temperature range. If that specific food source disappears or that specific environment changes dramatically, the specialist is toast. They have very few options. The generalist, however, the species that can kind of make do with whatever is available, the rat, the cockroach, the crow of their time, has a much better chance of finding something to eat or somewhere to live when the world gets turned upside down.
So, being widespread and adaptable were keys to survival. And when recovery finally happened, millions of years later, what did the new ecosystems look like? Were they just replicas of the old ones?
Almost never. When biodiversity eventually bounced back, the composition of that biodiversity was often radically different. We typically see a couple of key trends in the recovery phase. One is often a mixing of biotas.
Mixing of biotas?
Yeah, species that were previously restricted to certain regions might spread out and colonize new areas during the reshuffling, leading to ecosystems with species drawn from different places. And related to that, you often see a decrease in endemicity.
Endemicity. Can you remind us what that means?
Sure. Endemicity refers to species being unique to a specific, limited geographic area, like lemurs are endemic to Madagascar or kiwis are endemic to New Zealand.
Got it.
So a decrease in endemicity after an extinction means that many of those unique, locally adapted species, the endemics that defined particular regions, were often the ones that went extinct and didn't come back. They were replaced by more widespread, generalist species that could survive the crisis and then spread out.
So even if the total number of species eventually recovers, the world is less unique, less diverse in its regional character.
Exactly. That's a critical finding, especially for conservation today. Global species counts might, over millions of years, return to pre-crisis levels, but the unique regional ecosystems and the highly specialized endemic species they contained, once they're lost, they're gone forever. They don't just magically reappear. This really underscores why protecting localized biodiversity hotspots now is so incredibly important. Because when those unique pockets of life are extinguished, that evolutionary history, that unique genetic heritage is lost to the future. You can't unscramble that egg. It fundamentally changes the future trajectory of life on Earth.
Which brings us, inevitably, right back to today, to the present. We've journeyed through these immense ancient catastrophes. Are we actually listening to these echoes from the past? Because the scientific consensus seems to be growing, alarmingly, that humanity is either pushing us into, or maybe is already in, a sixth mass extinction.
That's right. The evidence is mounting, and the comparison of extinction rates is, well, it's stark, it's unambiguous. Remember that background extinction rate, the natural hum? Maybe 0.1 to 1 extinction per million species per year.
Right, very low.
The current rate, driven by human activities.
Okay.
Even the most conservative scientific estimates put it at 100 to 1,000 times higher than that background rate.
100 to 1,000 times faster.
At least. It's an acceleration unlike anything seen in potentially tens of millions of years, maybe since the last mass extinction. Just to give you a snapshot, the IUCN Red List, which tracks threatened species back in 2007, it already listed over 16,000 species at imminent risk of extinction, and nearly 800 confirmed extinct in recent history. And those numbers have only gotten worse since then. The speed and scale are truly alarming.
And the fundamental difference here, the core distinction from the Big Five, is the cause, isn't it?
That's the crucial difference. The Big Five were triggered by massive natural forces, colossal volcanism, asteroid impacts, continental drift leading to glaciation, forces entirely beyond the control of the life existing at the time. This current crisis, however, appears to be driven almost solely by us, by anthropogenic activity. Human activity is the primary engine.
What kind of activity specifically?
It's a whole suite of things acting together. Rampant habitat destruction and fragmentation, turning forests into farms, wetlands into cities, pervasive pollution, plastics, chemicals, fertilizers, overexploitation of resources, overfishing, overhunting, the introduction of invasive species that outcompete or prey on native life. And overlying all of this, rapid human-caused climate change.
So just like the past extinctions, it's not one single thing, but multiple interacting stressors.
Exactly. That's one of the most striking parallels. Past extinctions were rarely caused by just one factor. It was the deadly synergy, the cascade. And today, species are facing that same kind of simultaneous pressure from multiple angles. Human population growth puts pressure on resources, leading to habitat loss, while our energy use strikes climate change, pollution adds chemical stress, global trade spreads invasive species and diseases.
You mentioned new pathogens, like that amphibian fungus.
Yes, chytridiomycosis is a terrifying example. A fungal disease, likely spread around the world by human activity, that has absolutely decimated amphibian populations globally. Frogs, toads, salamanders, creatures that have been around for hundreds of millions of years, survived previous mass extinctions, are now facing unprecedented declines because of this one disease, on top of all the other pressures like habitat loss and climate change.
The fact that amphibians, these great survivors of past apocalypses, are now among the most threatened groups, that feels like a particularly loud alarm bell, doesn't it? Like a general message, as some scientists put it, that we might have little time left to avert something truly catastrophic.
It really does. Amphibians are often seen as the canary in the coal mine for ecosystem health because their permeable skin makes them so sensitive to environmental changes. Their current plight is a stark warning about the systemic stress Earth's ecosystems are under.
And the strongest parallel, the one that echoes most loudly from events like the Permian and Triassic, seems to be climate change itself.
Undeniably. Just as those ancient extinctions were profoundly driven by rapid global warming linked to massive volcanic CO2 release, our current crisis is being driven by rapid global warming linked to our release of fossil fuel greenhouse gases.
The source of the gas is different volcanoes then. Humans now, but the effect.
The ecological outcome, a rapid global climate shift happening much faster than species can naturally adapt, is a direct, chilling analog. It reinforces that universal lesson we drew from the past.
That it's the rate and magnitude of change that matters most.
Precisely. It's the speed and scale of disruption to fundamental planetary systems. The climate, the oceans, the land that drives extinction, regardless of whether the initial trigger is a volcano, an asteroid, or human industry. When change happens too fast, life can't keep up. Ecosystems unravel.
But here's the crucial difference and maybe the sliver of hope.
Exactly. This is perhaps the most profound and, in a way, the most empowering takeaway. Unlike all previous mass extinctions caused by forces entirely outside of life's control, this current crisis is the direct result of the actions of one species, Homo sapiens. And if human activity is the cause,
Then human activity can also be the solution, or at least can change the trajectory.
that's the logical conclusion. We have agency. We understand the mechanisms now, partly thanks to studying these past events. We know what drives extinction. Therefore, human activity can work to reverse this trend, as the researchers put it, through concerted conservation efforts to protect species and habitats, through fundamental shifts in how we use land and resources, and critically, urgently, through rapidly curbing greenhouse gas emissions to stabilize the climate.
So paleontology, the study of ancient life and death, it's not just about the past.
Not at all. It's a vital guide for the future. It provides essential, data-driven insights into vulnerability, which species traits make them susceptible. It shows us the long-term consequences of crossing planetary boundaries. It helps us understand the recovery process. In that sense, paleontology is a critical tool for navigating the present and preserving life for the future. It's a guide to avoiding the fate written in the fossil record. ### outtray changer.
Wow. Okay. This deep dive has been intense. It's really laid bare the sheer, almost terrifying power of planetary change. We've seen how the Big Five weren't just isolated incidents. They were these horrifying cascades, rapid, synergistic environmental shifts piling on top of each other.
Yeah, the triggers varied, asteroid, volcanoes, ice, but the result was the same. global ecological collapse.
It really drives home that Earth is this incredibly complex, interconnected system. It has tipping points. And when you cross them, the effects just ripple outwards across the whole planet, ignoring any boundaries we might draw on a map.
Absolutely. And the central lesson, the one that screams out from the fossil record for us, living now in what many call the Anthropocene, it feels unambiguous that today, for the very first time in Earth's entire 4.5 billion year history, one single species, us, humanity has become the dominant force driving a global scale crisis. We have, maybe inadvertently, maybe carelessly, kick-started the very same mechanisms.
Rapid climate change, ocean acidification, habitat loss.
The exact mechanisms that led to the worst extinction events the planet has ever seen. The paleontological record isn't just history, it's a mirror reflecting our current trajectory. It's a stark, urgent warning. And maybe, just maybe, a roadmap for how to change course.
It's definitely a stark reminder. While the planet itself will eventually recover, life finds a way. Over millions of years, the unique, intricate, frankly irreplaceable biodiversity that exists now, the result of millions of years of evolution that could be lost forever. Just like those Devonian reefs or the Triassic archosaurs.
Gone. A fundamentally impoverished planet for potentially eons to come.
So knowing this history, understanding these mechanisms, and recognizing our unique, unprecedented position as both the cause and the potential solution, the question really comes back to us, to you, listening. What steps can you take? What does learning about these deep echoes of extinction inspire you to explore further, maybe in your own community, or even just to change in your own daily actions, to help preserve the incredible richness of life that still surrounds us?
The past has delivered its verdict multiple times. The future, however, is still being written. And for the first time, the pen is largely in our hands. What story will we choose to write?